Data structures allow the RPG program to redefine a portion of the program's memory space. Suppose you have a date field in your program. If you want to access the month, day, and year as separate values, you will have to extract the three portions of the date field into three other fields that will be stored in three separate memory locations. If you create a data structure to hold the data field, you can redefine the data structure so that the same date field can also be accessed as three individual subfields that contain the month, day, and year. No new storage is needed for these subfields. A data structure is created during program initialization and is available only to the program that creates it. It is automatically deleted when the program ends. The data structure is treated as a character string. Although individual fields are allowed to be defined a numeric. By default, the data structure is always initialized to blanks unless otherwise specified. Let us look at how to define data structures in our program. Data structures can be defined either within the program or it can be externally defined. We will first look at program-described data structures. Data structures are defined on the input specifications. We code DS in positions 19, 20 to identify the beginning of the data structure definition. On the lines immediately following the DS entry, we code the subfields in the data structure. In positions 53, 58, we specify the name of the subfield, and in positions 44, 51, we specify the location of the subfield within the data structure with the from and to values. We can also provide a name for the entire data structure in positions 7, 13. This is optional and is useful only if we need to access the data structure as a whole in our program. The length of the data structure can be coded in positions 48, 51 of the line with the DS entry. However, if this field is left blank, the system will derive the total length of the data structure based on the lengths of the subfields. The fields of the data structure can also be fields defined elsewhere in the program. For example, as part of an input record. In such cases, the definitions must match since they are defining the same data item. Next, we shall look at externally defined data structures. This method is useful when the same data structure is to be used in more than one program. The data structure can be defined once and referenced by the programs whenever it is needed. To describe a data structure externally, we first create a physical file with the required fields that will provide the external description of the data structure. In the program, we define the data structure in the I specifications. In the columns 7, 13, we specify the name of the data structure. We code DS in positions 19, 20 to identify the beginning of the data structure definition. And E in column 17 identifies the data structure as externally described. Starting in column 21, we specify the name of the database file that is to supply the description for the data structure. Let us look at an example that uses a program-described data structure. We shall see how a data structure can be used to divide a field into subfields. We have an input file that contains the customer code and also the city to which the customer belongs. Our program requires the last 3 characters of the customer code and the first 3 characters of the city field. We can create a data structure through which we can access these fields. The customer ID and city fields are identical to the fields in the input record. Each time a record is read from the input file, the values will be stored in the data structure. The subfile CCODE contains the last three characters of the customer ID, while CCITY contains the first three characters from the city field. In this example, you saw how a data structure could be used to divide a field into subfields. Similarly, different fields can be grouped together into a single field. For example, from an input file, our program requires the order number and shipment date combined into a single field. We create a data structure that contains the two fields order number and shipment date. Our program can now access the two fields as a combined field by using the data structure name shipping code. Another situation where you would use a data structure is to break up a field into multiple array elements. For example, a database file containing sales information has one record for each salesman. The sales data for 12 months are stored in one large field. The best way of processing this data would be to use arrays, since all 12 sales data have the length and attribute. We can use a data structure to first divide the field into 12 subfields and then to map each month's data onto a corresponding array element. On the input specification, we define a data structure which has two subfields. One is the externally defined field SALDAT, that is also redefined as a subfield ARR. ARR is also defined on the E specifications as an array having 12 entries. The data structure maps SALDAT onto ARR. Sometimes fields are defined separately in the database file but are best processed using an array. We can use a data structure to group the fields together to form an array. All the fields in the database have the same length that also matches the length specified for the array. Data structures can also be used to redefine fields. One of the most common situations where this feature is used is in manipulating a date field. An application will often require the date in different formats, or maybe only a portion of it, such as the month, day, or year. For example, here we define a data structure that has a field date which is of length 6 characters. This field is also redefined as a numeric field DATEL, that is a numeric field with 0 decimal places. We also have 3 subfields DAY, MTH, and YEAR. DAY redefines the locations 1 and 2, MTH redefines 3 and 4, year redefines 5 and 6. In addition, locations 1 to 4 have also been redefined as DAYMTH. All of these subfields occupy the same 6 memory locations. Overlapping subfields cannot be used in the same calculation. Let us move on to multiple occurrence data structures. A multiple occurrence data structure is nothing but multiple copies of a data structure. A multiple occurrence data structure is very similar to an array in the sense that multiple values can be stored for the same field. All the copies have the same format and attributes. A multiple occurrence data structure is defined by specifying the number of occurrences in positions 44, 47 of the line on which the data structure is defined. The first data structure in the group has an occurrence 1, the second has occurrence 2, and so on. We can access each copy of the multiple occurrence data structure by referring to its occurrence per position within the structure. Let us define a multiple occurrence data structure. A student file contains the marks obtained by 5 students and also the attendance details for each student. For each student, there exists a different record for each term. An application calculates the total marks obtained by the students and also the total attendance across the different terms. A multiple occurrence data structure with 5 occurrences is used to process the student records. The data structure has 2 fields, one for the total marks obtained by the student and the other for the total attendance of all the terms. The program will read each record from the file and uses the value in the student number field to access a particular occurrence of the data structure. When all the records have been read and processed, each occurrence of the data structure will contain the total marks and attendance for each student. We can also create 2-dimensional arrays using multiple occurrence data structures. A student file contains the marks obtained by 5 students for 6 different subjects. There is a different record for each student for each term. Our application is going to calculate the total marks for each student in each of the 6 subjects. We have to define only a single array for identifying the 6 fields that are to be totaled for each student. This array is then included in a multiple occurrence data structure where each array will contain the DTA for one student. The occur operation is used to identify the particular occurrence that is to be updated with the totals using the value of the student number field. After all the records have been read and processed, each occurrence of the multiple occurrence data structure will contain the totals for each student. When using the elements of a data structure in your calculations, always make sure that the data structure is properly initialized. By default, the data structure is filled with blanks as the program always treats a data structure as character. If any of the subfields are defined as numeric, they should be explicitly initialized before being written to a database file. Otherwise, a decimal data error will occur. There are several ways in which you can initialize a data structure. The first method is by global initialization. For this, we enter an I in column 18 of the input specification. During program initialization, the numeric fields will be initialized to zeros and the alphanumeric fields are initialized to blanks. Another method is to initialize each subfield. Here you write an I in column 8 of the input specification for the field you want to initialize. Starting in column 21, you specify the value with which to initialize the field. Character values should be enclosed in apostrophes. When using this method, only the fields which have an I in column 8 will be initialized. We can combine these two methods so that all the fields will be initialized. With the initialization value specified explicitly for a field, will overriding the global initialization for that field. Initialization can be done on both program described as well as externally described data structures. Very often you will need to reinitialize fields during processing, such as setting subtotal accumulators back to 0 in control break programs. RPG creates two operations, clear and reset. The clear operation resets the value of the fields specified to 0 or blank depending on the field type. The clear operation is not restricted to data structures alone. It can be used with individual fields, arrays, record formats, etc. An entry is required in factor 2 that identifies the data item to be cleared. In the case of multiple occurrence data structures, only the current occurrence is cleared. In the case of a database record format, we can specify *no key in factor 1 to indicate that all the fields of the record except the key file are to be cleared. Also, only the output fields in the record format will be affected. The rest operation is similar to the clear operation. However, reset restores the data items to whatever values had been assigned to them during the program initialization step. In the next section, we shall look at some special uses of data structures. There are a number of special data structures that we can use in our programs. We have data area data structure, file information data structure, and program status data structure. Let us look at the data area data structure. We have already seen in an earlier chapter how to retrieve, use, and update a data area from an RPG program using the DEFN, IN, and OUT operations. The data area has to be explicitly read from the storage and written back. Instead, if we define the data area as a data structure, it will be implicitly retrieved during program initialization and updated when the program ends. A U in column 18 of the line that defines the data structure identifies a data area data structure. The name specified in columns 7, 12 must be that of an existing data area. Here we can define subfields, both character and numeric. We can also use the DEFN operation in addition to defining the data area as a data structure, in case we need to also update the data area explicitly. With data structures, it becomes possible to update a portion of the data area without affecting the rest of the data area. The data area will remain locked even after an OUT operation until an update is done through the data area when the program ends. Next we shall see file information data structures. When a file is accessed by a program, the system passes a file status buffer to the program. This buffer is called the input-output feedback area. The programs can access the information in the buffer using the file information data structure. A file information data structure is associated with a particular file. Every time an input or output operation occurs on the file information data structure is updated. To define a file information data structure for a particular file, we specify the infds keyword as a continuation option on the file description specification. In columns 60, 65, we specify the name of a data structure. In the I specifications, we define the fields of the data structure. IBM has provided some special values that can be used in the from and to columns to refer to frequently used fields. The special values are *file, *record, *opcode, star status, star routine. Corresponding field names for the subfields will have to be provided in columns 53, 58. The length of these fields is determined by the system. The field associated with star file will contain the file name. The field associated with star record will contain a record format name for externally defined files and a relative record number for program-described files. The first 5 positions of the field identified by star opcode are used to describe the current operation. The last position indicates whether the operation was performed using a file name or record format name. Star status contains an error code that identifies whether the previous operation completed successfully or not. A value of 0 indicates that the preceding operation completed normally. Any other value identifies a specific error, such as duplicate key not allowed or record number not found. Star routine identifies the point in the RPG cycle at which the file was accessed. The file status data structure contains a lot more information that can be accessed by coding the location of each subfield in the from and to positions. This information can be found in the reference manuals. Let us move on to the program status data structure. The program status data structure is used to retrieve information about the program itself, including errors that occur during program execution. A program status data structure is identified by an S in column 18 of the input specification that defines the data structure. Here also, you have predefined values that can be used to access the more frequently used subfields within the data structure. Star PARMS contains a count of the number of parameters passed to this program by a calling program. Star PGMNAM contains the name of the program in which this program status data structure is defined. Star routine and star status are the same as in the case of the file information data structure. The program status data structure contains a lot more information such as the job name, username, system date, etc. that can be accessed by coding the location of each subfield in the from and to positions. This brings us to the end of the chapter on data structures. In this chapter we saw how to define and use data structures in RPG programs. Data structures can be defined both externally as well as within the program. Data structures can be used to group fields as well as to divide a field. We also saw how data structures can be used with arrays. We looked at multiple occurrence data structures. And finally, we saw some of the special data structures like data area data structure, file information data structure, and program status data structure.